Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at implicit differentiation, so we can answer questions from exercise 9H. So, implicit differentiation involves differentiating functions that are a mix of x and y letters. So we're going to see first just a reminder of how we differentiate with respect to x. If we're differentiating this x function here, it's x squared, the function, with respect to x. Then we get an answer of 2x. If we differentiate sine x with respect to x, we get cos x. And if we differentiate e to the 3x with respect to x, we get 3e to the 3x. And notice here how the function has the same letter that we are differentiating with respect to. It's all x's, there's no different letters that are happening there. But what we're going to look at in this video in particular is how we differentiate y functions, such as y squared here, with respect to x. Now notice here how the letters don't match up, they're not the same type of letter. So the little trick that we do is we're going to effectively treat these as fractions now and times it by dy by dy. Now if you times by a fraction equivalent to 1, you don't change the calculation, you're just going to change it up a little bit. So dy by dy. And we're then going to swap over the dx and the dy. And remember that if you're multiplying fractions together, it doesn't matter the order in which you're multiplying, you can change these round as you wish. So what this is going to now become is d by dy of y squared times dy by dx. And now all of a sudden in this space here, we are now differentiating y squared with respect to y. That is now the correct letter that we are differentiating with respect to. So we calculate this bit that's in a square. So the differential of y squared with respect to y is 2y. But then all we have to do then is just to times by dy by dx. So if you're differentiating a y squared function with respect to x, you differentiate it normally, 2y, and you times then by dy by dx to take into account the fact you are differentiating with respect to the incorrect letter. Your function is y here, your letter is x, you're differentiating with respect to, that's the incorrect letter. You would quite like it to be a y, that's the correct letter. So dy by dx balances that all out. Okay, let's have a look at the second one then. Differentiating sine of y with respect to x. So the trick that we do here is we times by dy by dy, swap over the denominators. So it's now d by dy of sine y. So we're differentiating sine y with respect to y now, times dy by dx. So this is going to equal the derivative of sine is cos, so it's cos y, times dy by dx, to take into account we're differentiating with respect to a different letter. So hopefully a pattern is emerging in our answers here. Let's have a look at the next one. Maybe you might be able to predict what the answer to this is going to be. Differentiating e to the 3y with respect to x, we times top and bottom by dy by dy. Swap over your denominators and it becomes d by dy of e to the 3y. So we're differentiating e to the 3y with respect to y, and times it by dy by dx. So the answer here, the derivative of e to the 3y is 3e to the 3y times dy by dx. Now you don't need to do this whole process every single time. You can, now that we've started to spot the pattern, just jump straight to the answer. Now what is the pattern here? Well, we've seen here that if we differentiate y squared, we get 2y. If we differentiate sine y, we get cos y. If we differentiate e to the 3y, we get 3e to the 3y. But then because we're differentiating with respect to x, a different letter to the function that has the variable of the function, we times by dy by dx on the end. So if you're differentiating an x function, differentiate normally. If you're differentiating a y function, differentiate normally, but bung a dy by dx on it at the end. So the general rule here is that if you're differentiating a function of y with respect to x, the answer is the derivative of that function with respect to y, but you times by dy by dx afterwards. Okay, so that's the rule that we're going to be basically using for this video here. X functions differentiate normally, y functions also differentiate normally, but times by dy by dx on the end. Okay, so you also need to be able to use the product rule, quotient rule, and chain rules alongside your implicit differentiation. So just going back to a bog standard product rule type question here is, if we have e to the x sine x, and we want to differentiate it with respect to x, then we go through the whole product rule formula. You set up your f of x function, your g of x function, differentiate both of them, do a bit of cross multiplying and addition. And your answer here is going to be e to the x sine x plus e to the x cos x. But let's see how this would work if your function was e to the x sine y with respect to x. So you would set up as normal. Your first function would be e to the x, differentiate that, you get e to the x. Your second function, now strictly speaking, we shouldn't really write the x here, we should probably write a y, but the g function is sine y. And when we differentiate that with respect to x, we're going to get differentiated normally cos times dy by dx. And now we're going to input this into the product rule. So using exactly the same product rule that we had before, it's going to be f dash of x times g of x plus f of x times g dash. So it's going to be equal e to the x sine y plus e to the x cos y dy by dx. So when you do differentiate using the product rule, you can have dy by dx's appearing throughout your equation. Okay, let's move on to some questions now then and see this implicit differentiation in action. So below is a sketch of the curve x squared plus y squared equals 25. And the question is, find the gradient of the curve when x equals 4. So we want this gradient here and this gradient here. So we have two different answers. Okay, and just from substituting in x equals 4, we can work out that the y coordinate is going to be either 3 or minus 3, and that's definitely going to help us in the next part. Now what we're going to do is we're going to effectively take the x squared plus y squared equals 25 equation and differentiate it. Differentiate the whole thing. Effectively, we are differentiating each term with respect to x. So the x squared gets to go first. That differentiates to 2x. The 2y now, sorry, the y squared now has to be differentiated with respect to x. So we differentiate it normally and times it by dy by dx because we're differentiating to a different letter. And the 25 here will differentiate to 0 because if you remember, numbers always just differentiate to 0. Now we're looking to find the gradient. So what we're going to look for is an equation where it has dy by dx equals something. So we want to make this dy by dx the subject. So if we take away 2x onto the other side and divide by 2y, this gives us exactly dy by dx equals something to do with x and y's. Simplify this and we get minus x over y. So now what we can do is we can substitute in our numbers for x equals 4, and remember we worked out that the y coordinate was equal to 3. So substituting in the higher coordinate, 4, 3, we're going to get the gradient of minus 4/3. And substituting in the higher coordinate, the one down, so the lower coordinate, the one down here where the coordinate is 4 minus 3, we substitute that in and we get 4/3. So you can see here how the two gradients compare to each other. One is obviously going downhill, one's obviously going uphill. So there we are, we can now differentiate equations the whole way throughout that equation. Let's have a look at differentiating this function here. Find dy by dx in terms of x and y. So we're going to start with the function and differentiate with respect to y the whole way across that equation. So the x cubed term will differentiate to 3x squared. X will differentiate to 1. Y cubed, now it's a different letter here, y cubed will differentiate to 3y squared dy by dx, plus 3y will differentiate to, with respect to x, it will differentiate to 3, differentiating it normally, but because it's a different letter, dy by dx will need to be multiplied on there, equals, and then 6 differentiates to 0. What we're looking for now is to find dy by dx as made the subject on its own. So we're going to need to take away 1 and take away 3x squared onto the other side. They don't have dy by dx in it, so we can subtract them. Then we're going to factorise out dy by dx to help make that the subject. And we're going to divide by its fraction, divide by its factor. So 3y squared plus 3, we're going to divide by all of that. So dy by dx equals minus 1 minus 3x squared all over 3y squared plus 3. So there we are, that's how we find dy by dx in terms of x and y when we have a function that is x and y's throughout. Right, a much more difficult question here because the x's and y's are now starting to get mixed up with each other. 4xy squared plus 6x squared over y equals 10. Find the value of dy by dx at the point 1, 1. So in this question you have two functions multiplied in the first term and a division of a function in the second term. This means we're going to need to apply our knowledge of the product rule and quotient rules as well. So, starting on the 4xy squared, we're going to need to use the product rule for this term. F of x is the 4x part, so we're splitting it into two parts here. The 4x part and the y squared part. So 4x would differentiate to 4. G of x, or g, I wouldn't call it the g of x, I'd just call it the g function is y squared. The differential of that is 2y dy by dx. And now we're going to substitute it into the product rule. So this here is the product rule, and substituting this in, we're going to get, I don't really like that bit there, we'll scribble that bit out. We're going to get f of x, that's 4x times by the derivative of g, so that's 2y dy by dx, plus the derivative of f, which is 4 times the g function, which is y squared. And simplify this, and we're going to get 8xy dy by dx plus 4y squared. So that's what 4xy squared differentiates to. We've got the first part of our differential of this whole equation here. And now we need to work on the 6x squared over y as a quotient rule. So the top of the fraction is 6x squared, derivative of that is 12x. The bottom of the function is y, and when we differentiate that, we're going to get 1 dy by dx. Remember, we're differentiating to the incorrect letter there, so we need to times by dy by dx afterwards. Now let's apply the quotient rule. So this is the quotient rule. Let's apply it and simplify all the terms. 12xy minus 6x squared dy by dx all over y squared. So putting this all together now, this part here differentiates to this part here, and this part here differentiates to this part here. So we've used the product rule on this bit here, and we've used the quotient rule on this bit here, and obviously 10 just differentiates to 0. Right, we've still got a lot more work to do then. We need to work out dy by dx at the point 1, 1. So, rather than rearranging, what we could do actually is substitute in the x and the y values now. We don't just have to rearrange to make dy by dx the subject, we can substitute in the coordinates at any time that would be most beneficial to us. I reckon we substitute in the 1, 1 coordinate in x and y now. Dy by dx won't be replaced by anything. So substituting in x equals 1, y equals 1 in every single position on this equation here. Simplify your answer and collect like terms, and we can see here that obviously dy by dx equals minus 8. There we go, that was a really difficult question there, but when you break it down into its separate components, it's It's really not too difficult. Final one then, find the value of dy by dx at the point 1, 1 when e to the 2x ln y equals x plus y plus 2. So use the product rule to differentiate the left hand side. So e to the 2x differentiates to 2e to the 2x. Ln y will differentiate to 1 over y dy by dx. Put the two together and we're going to get e to the 2x times 1 over y dy by dx plus ln y times 2e to the 2x. And we can simplify this to this. And what we're then going to do is now effectively apply this on the left hand side. So we've differentiated the left hand side. We've still got to differentiate the right hand side. So x differentiates to 1, y differentiates to dy by dx, 2 differentiates to 0. And probably the next thing to do here, so remember what we've done here is we've differentiated and this was our answer here, effectively using the product rule. So now what would be a good idea is to now substitute in the coordinates of 1, 1. So substitute in all the coordinates of 1, simplify and collect like terms. We're going to have to get all the dy by dx's onto one side so that we can then factorise it out. But then divide by e squared minus 1, and we get 1 over e squared minus 1. So there we are. Right then, so your turn to have a go at these two questions then. Pause the video and try these two questions out. So let's get started on the first one then. So y cubed is going to differentiate to 3y squared, but it's a y function, so that needs a dy by dx on it. Now the second part here, that needs the product rule on it because it's got both x's and y's in it. So I'm going to do the product rule straight away into the equation. I'm going to differentiate 3x squared first, that's 6x, and then times it by the original g function, that was y. So I'll split it into two parts here. And then the second part, I'm going to keep the 3x squared the same, but differentiate the y function to dy by dx. It would differentiate to 1 normally, but remember it's a y function, so it needs a dy by dx on it. The last part of this equation here is 4, is minus 4, because minus 4x differentiates to minus 4. Okay, what we can do now is we're going to need to group together the dy by dx's by factorising. Everything else is going to need to get moved onto the other side. So dy by dx, we have a 3y squared multiplication of that, and we have a 3x squared multiplication of this. And the other bits are going to get subtracted or added onto the other side. So I've done quite a lot of steps here. I've subtracted that onto the left, I've added this onto the, so I've subtracted this onto the right, I've added this onto the right, and I've factorised the other two bits together. Now I'm going to just divide by the fraction, so I'm going to get 4 minus 6xy all over 3y squared minus 3x squared, and there we are. That's our final answer. For question 8 here, slightly more difficult, 3 to the power of x. Well, can you remember how to differentiate 3 to the power of x? The way you would differentiate that is 3 to the x times ln 3 equals, now on the right hand side, y differentiates to dy by dx minus, and then 2xy will need the product rule on it because it's got a combination of x's and y's. So the 2x will differentiate to 2, and then we'll have 2 times y. So I've differentiated the 2x to 2. Because I've differentiated an x function, I don't need a dy by dx on it. It just differentiates normally. So 2x differentiates to 2, keep the y function the same. And then I'm going to have 2x staying the same, but I'm going to differentiate the y function, and that is dy by dx. So there we are. So we've now want to find the exact value of dy by dx. Okay, So what we'll do is we'll plug in x equals 2 and y equals minus 3. So let's go for it. So we're going to have 9 ln 3 equals dy by dx minus 2 times minus 3. That'll make it plus 6 for this bit here. And then it'll be minus 2 times 2 is 4 dy by dx. So let's group the dy by dx's together. And we're going to get minus 3 dy by dx's plus 6. So what I suggest we do is we add the 3 dy by dx's onto the other side and take away the 9 ln 3. We can then divide the whole equation by 3, so we're going to get 2 minus 3 ln 3 as the gradient. Okay, there we are. That's all that there is to implicit differentiation. Have a go at plenty of the questions from exercise 9H. It does require lots of practice, but when you can break it down into small manageable differentiation differentials, it's not too bad really. So have lots of practice, have a go at the problem solving, the exam style questions, and ask your teacher for help if you need any. Thanks very much for watching.